Next up we have with Moon. Anybody here not know Cliff? Check it out. 1, 2, 3, 2. Awesome. Okay, so you all know Cliff. For those of you that don't know him, the three of you, Cliff is co-founder at Boundary?
Yeah, founder and CTO.
Yeah, there you go, at Boundary, and it's been online for pretty much forever. Is harking way back to when we started the day. He's going to be talking about what you actually do when stuff starts going wrong, basically. Deal with it.
Yeah. So, howdy everybody. Yeah, I'm Cliff, and I'm from Boundary. You'll have to excuse my voice, I'm getting over being sick. So Boundary, just a quick plug. We do network monitoring as a service, and we have a booth downstairs. Please come by and visit and check out lots of pretty pictures about what's going wrong on your networks. And that's my sales pitch. Thanks. So Whack-A-Mole. Everybody familiar with this game? Does anybody not know what Whack-A-Mole is? Yeah? So one mole comes up, smack it on the head, 2 more pop up. That's basically performance tuning, right? So this talk is about my own personal production experience, and so I sort of want to qualify everything here. I'm not giving you sort of anything generic or anything that may apply to your stuff. Your mileage may vary. This is all folklore, right? Like these are things that help me. They may or may not be true, and they may or may not have actually had an effect on what I was doing at the time. But when you get woken up in the middle of the night, you'll try anything to get the software to quiet down, right? And so, and also the other sort of meta note here is that, the version Erlang for most of this stuff is R14b04, but when I've made claims about what Erlang does under the hood, I've checked up to R16, and most of it's still true. And also, this talk is very much down in the weeds. So if you're not geeking out about the internals of the VM, you should probably head out. So, yeah. So anyway, folklore, right? I'm just a shaman trying to, assert some sort of primacy over nature, right? So, so the collectors. So at Boundary, what we do is we take in a ton of data from our customers, we process it, and and we have to be basically up all the time, or as much as possible, because we're a monitoring service. Our customers rely on us to keep their systems up. So, so the collectors, what they do is, first of all, it's the oldest piece of code, oldest piece of running code in our environment. What they do is they terminate the SSL connections from our customer meters. So, customer has a bunch of meters. They connect up to us. They start spewing out data over an SSL connection. We parse the SSL certs. We pull data out of there in order to figure out who's who. So we don't have to trust you when you say you are a certain customer. And then what it does is it takes this format called IPFix, transforms it into an internal format based on Erlang term protocol, exposes pub sub interfaces, and then uses another library that I wrote on the Scala side called scaling, which I talked about last year or the year before, to talk to basically to build a big Erlang distributed cluster of Scala nodes and Erlang nodes all sort of working together to process a bunch of data. So cool. So yeah, 2.5 years in production. This code base. It was one of the first things that I wrote for Boundary, and so the early versions were pretty crappy. Fell over at about 700 connections or so. Benched out at about 10,000 records per second before it would start, slowing down and causing some issues. And so today, actually just benched it out yesterday, and we're currently handling somewhere around 3,000 connections per machine, 300,000 records per second per machine. To qualify, a record is somewhere around anywhere from 50 to 80 bytes a piece. So plus some overhead, you can do some math. Anyway, the throughput as measured from Boundary is about 100 megabits per second ingress per machine, and then 300 megabits per second egress into our internal network. So on the pub sub interface. So these guys, they're doing a lot of stuff. That's still too slow, actually, but it's it's better than it was.
Same hardware?
Yeah, same hardware. Mm-hmm. So Erlang. There's always a queue somewhere getting backed up, right? This is how I feel. And if anyone was at Jeff's talk earlier today, a lot of this will feel very similar. I'm sorry if I'm rehashing the same stuff, but It's probably things you should hear again anyways. So if we're trying to find the queue that's overflowing, what do we use? How do we get there, right? Like, so I'm just going to assume that, does everyone here know remote shell? Yes? Anyone here not know what remote shell is? Okay, that's probably the better question. So remote shell is absolutely magical. It's one of the best things about Erlang, and one of the things that no one talks about outside of the Erlang community, which I think is crazy. You get a remote REPL into a production system, and you can run arbitrary code, which is frightening and awesome at the same time. These are some of the things that I use when dealing with my production systems. So that I function up there, oh, sorry, I'm in the way of stuff. That I function up there, that'll actually print out the process table. It's like PS for your Erlang. ETOP, if you can get it to work, I've never gotten it to work quite properly, but it works really well with React, which is nice. Process info, so you can actually, so here's a nice little hack. So you can actually say PID and then give it 3 numbers and it'll transform it into a PID for you. That's fun. So you get process info. You can also get a backtrace. I don't know if you knew that, like all the way back to R14, like even without the new exception stuff. You can get a backtrace, print it out to the console, and actually figure out where the call stack is. So that's really cool. You should use that. And so other stuff here. So that's top stuff. That's all runtime. You got woken up. Oh my God, what's happening? Everything's on fire. This is stuff you do beforehand, right? So you got to make your own escape hatches. So when you build stuff, you need to build it with the idea in mind that at some point you're going to be running around like with your head on fire and you're going to want to break encapsulation, right? So basically what I do is any single gen server or anything that I build, I will just have state clobbering methods. Hi, haters. And then admin functions, right? So like, if you find yourself doing the same thing over and over again when stuff catches on fire, you write admin functions and ops playbooks so that when someone other than you gets woken up, they'll have some idea of what to do. So the escape hatches, yeah. Clobber state, right? Can people read that? I'm sorry, I was not expecting a projector that sucked. So basically just handle call, clobber the state, or get the state out of a gen server, right? Because there's no way to inspect that at runtime that I know of without actually just sending a message and getting something back. Here's a fun one from our collectors. I'll post this code up later since this is all screenshots and stuff. But anyway, admin functions. So what these do is they dump the memory of the usual suspects, right? Like there's 2 things that are going to overflow at any given point in time. So when things are going wrong, what do? Remote shell in, and then admin meter memory, and then admin sub memory, and it lists them in order of who's consuming the most heap up at the top. So immediately okay, here's the guy, and oh my God, he has a gig of memory. Holy crap, we're gonna die, right? So playbook, admin stuff, this is all necessaries that you won't have on day 1, but you should develop as time goes along, right? DevOps. Anyway. So failures, right? Like how do Erlang processes fail in production? I will tell you how they failed for me. Typically what you see is there's some sort of overloaded process, right? And we're going to go through the ways I've seen overloaded processes go ape. So basically the generalized version of this is that for some reason an overloaded process cannot keep up with its incoming rate of messages. And the Erlang memory model makes this problem really bad, in my opinion. So the heap per process, that part's fine, but the message queue being stored on the heap makes this thing worse, and I'll tell you why. Because the problem here is that garbage collection puts the process to sleep. And if your heap is being consumed by the queue, guess what's going to happen? You're going to do more GC. And you end up in this situation that I like to call the process death spiral. And people who were at Jeff's talk earlier, this is a bit more of a dissection of what actually happens. But basically, at any given point, for any given process, let's say it can do n messages per second. If the arrival rate is greater than n, then the messages are going to start queuing up. And if that persists for long enough, then the queue will get larger and larger, and it causes the process to go into the garbing state, which I don't know everyone here has dealt with a crash dump, right? Yeah? Okay. Yeah, so garbing, we'll have a slide on that. But yeah, it'll cause it to go into the garbing state, which basically means it's garbage collecting and possibly reallocating as well, which is the fun one. And basically what happens is that as time goes along, it spends more and more of its time slice in garbing. But the sender doesn't stop sending messages. And so not only can your process not keep up at a baseline, it's getting slower as time goes along. This is terrible. And so basically, as time goes along, you can do less. You can do less messages per second, and so this problem gets worse and worse and worse until eventually you end up with a crash dump. And you see a lot of processes in state garbing. So this is from the Erlang docs where they talk about what do the different process states mean, and I've always found this to be hilarious. This is bad luck. This is bad luck. You happened to catch the process garbage collecting. Lucky you. No, actually, the process was like 90% of its time in garbage collecting. You're not lucky. But anyway, so this continues, and then the similar slide to Jeff's earlier. But eheap it asks the operating system for 8 gigs of RAM, and it's just like Malik is just like, sorry, dog, I can't help you, and yeah, and that's where that ends up. So, okay, cool. That's how things go terribly wrong. What do we do about it, right? So basically, there's 3 reasons in my mind, 3 generalized reasons of why you can't keep up. Either you're putting your process to sleep by calling receive somewhere within the main loop of the gen server or whatever it is. You're doing too much work, which in Erlang usually means math. Or your sender is just too damn fast, right? Like, one of these things has to give. So how do we mitigate? How do we mitigate this thing? And so for the various failures, so like how do we mitigate the receives? So I have a quiz for you. Receives in gen server. Which of these can cause a receive? Who votes for 1? No one thinks yeah, okay. 1s, okay. Who votes for 2? Any votes for 3? How about all 3? Anybody vote for all 3? Yeah, okay. Yeah, so it's all the above. All of these statements can actually incur a receive. And the first 2, that makes sense, right? Because underneath a gen call, you're receiving a reply back, right? Gen TCP receive, you're actually receiving a message from a port somewhere underneath the hood. But the send operator, what the fuck? So that actually, so if you look deep down inside the ERTS, you're going to find this code in erlang.url. And so this is actually from R16b. I made sure, I was looking at the code today, made sure this still existed. So inside of erlang.url, there's this function called desend. And if you look at biff.c, you'll find where it converts the bang operator into a send. And under certain conditions, not all of which I actually understood from the C, but under certain conditions, I think mostly having to do with the fact if the port is a remote PID, if it's a remote PID or a remote name and node, the name and node tuple. If it's either of those things, it can cause this to happen here, which is the desend, which degenerates into a netkernel connect and an Erlang send. The problem here is that netkernel is a gen server under the hood. And so you're actually doing a gen server call with a default timeout inside of the bang operator. And that only happens if you're calling a remote node, right? So it degenerates into an Erlang send so basically it's a gen server call and an Erlang send. So yeah, and I actually found this by profiling it out and like where the hell is the receive? And finally, that was a bad week. That was in like 2011. That was bad. Yeah, so that stinks. And so if you're sending something to a remote node, use Erlang :send because you don't want to get into the netkernel stuff. Yeah, cool. Other ways to mitigate errant receives. What I found is very, very good thing to do is separate the control plane from the data plane, and we'll get into that in a moment. You got to know what you're calling, right? So if you're using third-party APIs, you have to understand, what are they doing under the hood? Are they talking to other gen servers? Is this a nets table? I mean, you really have to just know all your code. Like, I wish Dialyzer would just have a mode that says, follow all the code paths and find the damn receives. That would be cool. Or it might, I don't know, that thing's huge. But, and then basically, with your own gen servers, like find the hot path and cut it down to as little code as possible so that you don't need to do as much static analysis beforehand to make sure that you're going to be all right. So what do I mean by separating control plane from data plane? Basically, control plane and data plane have, these are sort of generalized terms, but what I mean here is that the control plane is something that needs to be low latency, and the data plane needs to be high throughput. So these are at odds with each other, especially if they're pulling off of one queue. And so the basic way to do this, the basic way to do this is separate out in two processes, and then glue them together with a nets table. Basically, you set read concurrency on the nets table, and then away you go. So what we did here is that, if you remember earlier, one of the things that our collectors do is that they have a pub sub interface internally. So that pub sub interface multiplexes on both the customer name and a number of topics per customer. So if we have, somewhere in the area of several thousand customers and, say 5 topics per customer, and then we have a number of downstream machines that need to that need to subscribe to a bunch of that stuff, we're going to have a lot of subscriptions in that table. The problem, though, is that when one of those downstream machines dies, goes down for some reason, its JVM blows its heap or whatever the hell's going on, then we're in trouble, because then we have several thousand subscription requests incoming to the thing that's handling the high volume data plane. So yeah, that's really, really bad. And so that's basically when you want to pull apart that state. That thundering herd, right? It's a thing. So doing too much stuff, right? This is kind of the one that you always end up with. You're trying to put 10 pounds of shit into a 5-pound bag, and then that doesn't really end up going so well. So obviously the preferred solution is do less stuff. So I don't know if you noticed earlier, I sort of sailed it by you with my numbers, but our ingress is 100 megabits per second, but our egress in the back end is 300 megabits per second. So the astute observer would say, what are you doing between here and there to make that bigger than it was coming in, right? And so part of that is, a little bit of that is replication, but most of that is actually just inflation in the format to make it self-describing. And to give you an idea of earlier versions, it was 10 to 1. So we did some changes to the internal format about a year ago, cut that down by half, and bought us about 6 months of good runway to keep these things running. And so that's basically that's what you want to do. Obviously these changes are harder, but you want to do less stuff. Spit out less data, do less math, touch things less, because that's the easiest way to deal with performance problems. Sometimes you can't, though. Sometimes you have to mitigate the overload. So what do you do in Erlang? Well, there's sort of the flip thing here is to just say just spawn a process, right? So you're in a gen server, you're in a gen server call. You have some piece of work that either needs to talk to another gen server, or needs to do something long running, or do something that generates a lot of garbage. And those are important things to actually profile and understand, because say you're in a say you're in a gen server, and what you're doing may not take a whole bunch of time, but you generate this tremendous spew of garbage. Well, every so often, that gen server has to go back into garbage collection, and the garbage collectors in Erlang really stink, because mainly the whole thing is oriented around the fact that you should just be spawning off these short-lived processes to do this kind of work. Spawning off the process actually ends up being a cheap operation most of the time, and it can be cheaper than incurring all these garbage collections. But the important thing is that there's a price to be paid, which can be context switching overhead, right? So there's copies involved here, and you need to copy data from one place to the other. And then obviously spreading the load across CPUs can can also incur some overhead as well, right? And so the thing here is that you have to measure this, make the change, measure the effect, because you don't actually know what's going to work before you do it. You have your theories, and then the system will actually prove you wrong. Another way to do it is worker pools, which are actually a bad idea in Erlang because of that before mentioned GC problem. Processes are lightweight, and so this idea of having a pool for something is really just sort of a bad idea that that can be a holdover from other languages and other runtimes because spawning is so cheap. And really, the worker pool is only really useful when you have expensive stuff you're trying to wrap, like a socket, like a NIF, like a port, something with significant setup and teardown costs that you don't want to be, flapping up and down all the time. And then another thing you can do here, I hate to even mention it, but you can screw around with the process options, right? So, and I've definitely done a lot of this, and mainly I found it to be shooting myself in the foot when I've actually measured it. So you can set things like minimum heap size, you can set things like full sweep after, you can set the priority of the process. Most of them are just going to end up being either a step backwards or equivalent to what it was already doing. They don't really help out a whole lot. And in some cases, then it's just sort of a trap you've set for yourself, like that's going to go off a month down the road. In any event, you got to test and measure them if you do want to make those changes, but that's not where you're going to get your performance gains from. So that's a lesson that you don't have to learn. Of course, the other end of things is that you can always write. At the end of the day, you can always write a NIF, right? Obviously, you can do the work faster. You get access to system calls, so if you need to do things like writing the files, you can set the proper modes, map things, do all sorts of fun stuff. Of course, this starts that slippery slope down to a bunch of C++ glued together with Erlang. I'm looking at you, Basho. I kid. Okay, so fast senders. What do we do about the fast sender? Well, flow control, right? So, and depends upon what the sender is how we do our flow control. So we could be reading from a socket, and obviously, as has been drilled into many folks, use active once. I was not using active once for a while in this code. I thought, oh, I'll just set active true, and then I won't have to go to the trouble of setting active once because that's just going to slow me down. It's work I'm not. And then suddenly we had customers start up that were spewing gigabytes of data per day on a single node, and 10 megabits per second into a single Erlang process, right? From a single meter, like crazy shit like that. And we had customers that would spin up with these nasty data streams that we can only deal with on one process. And what? Active true is not helping us out there. So yeah, we're using active once. And here's the thing, use one of the actives though. Do not use GenTCP receive because one of the main reasons why is because GenTCP receive is a blocking call. And typically what you want to be doing is you want to have the messages delivered to you as fast as you can consume them. You don't want to be going back to the queue and trying to receive something and doing some sort of selective receive against it. You just want to work the queue head to tail fast as possible. And then use the framing socket options so that you don't have to do your own framing. With our protocol, I have to do my own framing. Ha ha ha, joke's on me. And I mean, basically the great thing about active once is that you leave the buffering to the TCP kernel. The great part about that is when you leave the buffering to the TCP stack in the kernel, it is able to exert back pressure through the TCP links to the sender. TCP has these really cool options, has this really cool stuff it can do with the window size, where basically, you have a TCP buffer size of however many K, and then once that gets overrun, the window size is set to 0, and it will tell the other side to shut up. And so long as there's no timeouts on that, so long as nothing times out and says, oh, this is done, and cuts the connection, it'll stay like that basically forever until you process your queue. So there is help. There's help available. TCP is nice. and then if you're doing process-to-process messaging, you can find in the mailing list allusions to flow control and back pressure inside the VM. I don't buy it. It all seems a little bit too magical and ill-documented. So basically what you want to do is to have your control. You want to basically implement your poor man's TCP inside of the protocol between your nodes, right? So again, what Jeff was talking about earlier in his talk, you make a request for a certain amount of data, the sender sends that amount of data to you, you process it, then you make a request again. And that ensures, because you're making the request, that ensures that you're able to process data at the rate that it's getting sent. And so you don't end up in that position where you have the buffer overspill. Yeah. And then the built-in flow control. So Erlang send, when you're sending to a remote node, sometimes that can suspend your process. So that is the one piece of built-in flow control that you don't really know about until you read the docs closely. So if you're sending to a remote node and suspending the sending process is not an option, you need to use send no suspend. Send no suspend will return an error value instead of putting your process to sleep. So if you're on the far sending end of a data pipeline and you need to send stuff across the wire, the buffer's full, instead of the buffer's full, like even if like the Erlang distribution buffer's full, no suspend will make sure that you don't put that process to sleep and then cause the cascading failure of death. And it's like, it's the question, like at the end of the day, what's better? Lose a little bit of data, wait to send, or gigantic explosion, right? Like lose all the data. You got to contain the pain. And then, of course, the one thing that I like to do here, and again, this is kind of hard to read, so I apologize, the blow-off valve. So memsup, is everyone here familiar with MEM-SUP from the OSMon package? Okay, so memsup actually works. It's surprising, it works really well. It has hooks into the ERTS, so it actually looks at allocations. And so you can register an event, so if you start up memsup, swap in an event handler, your own event handler into memsup, then you can the call is set procmem high watermark, and then give it a percentage of main memory. So this one is set to 2% of main memory. So what that's saying is that anytime a process tries to allocate more than 2% of main memory as its heap, alarm the event handler and let me deal with it. And then the coolest thing is inside the event handler, you get the message and then you get the PID of the process. And so you can actually inspect the PID to say, what the hell is this thing that's trying to take up all my memory? And then you can actually do real mitigation in there, right? So you could shoot the process in the head, obviously, which is pretty cool. Or you could, you could do any number of things depending upon what the actual goal is. Obviously shooting the process in the head is one thing. You could spin up more processes. Maybe that'll help. I don't know. Or you can just basically, like, if you have access to the sender, you can put the sender to sleep or tell the sender to slow the hell down. Like, there's things that you can do to keep this death spiral from spinning out and going out of control, because you can execute arbitrary code here. And it actually works, which is cool. So yeah, so stop the VM killing's death spiral of memory. So that's really cool. Moving right along, let's say that your Erlang app is mysteriously unresponsive, right? So we're out of the realm of memory consumption, CPU consumption, even disk consumption. Resources across the board, low utilization, and yet nothing is working. What is happening? Well, you're probably deadlocked. And so I'm going to ignore the classic case of deadlock where you have two things depending on each other and they're both waiting on something, because if that's what you're doing, then God help you. You shouldn't be writing code, honestly. But basically what can happen here with deadlock, you can get into some very interesting cases. And again, we get back to the generalized form. Like, within a given time period, a gen server can process n calls, right? So if your code sends at m, where m is larger than n, then m minus n calls will fail, right? Because the timeout happens. If you don't deal with it, the failures will propagate to whatever's making the calls. Let me illustrate this. So, and it all ends up being timeouts, right? So, and this has bit me so many times because there's a default timeout on gen call. So if you don't set a timeout, one is set for you at 5 seconds. Is 5 seconds the right value for timeouts? I don't know. It's one of those things. And so, the knee-jerk reaction is to set the timeout to infinity. That can actually make this problem worse because then you're waiting forever for something that might not get there, especially if it's a remote call. And so basically what you have to do here is, first of all, set a timeout that makes sense for your application. You probably don't even know what that is, so maybe 5 seconds is right. But you got to handle the failures, which is the important parts. Don't just let the process die. Do something about it, please. I know this is heresy, right? But you log the error and then maybe retry the call if appropriate. Again, we ran into this issue where back when I was talking about the control plane and data plane. So what would happen is that we'd have this situation where we'd have things trying to resubscribe to the subscription controller, and they were getting backed up. And there's this big backed up queue of stuff waiting to get done, and the subscription requests were sitting in the queue waiting to get done, and then they would keep timing out because there was a 5-second timeout set at the other end. And so the subscription would eventually go through, but the other side wouldn't recognize it because the call timed out, and it would keep trying to resubscribe to a subscription that was already there. And this condition would persist and go on and on and on, and it would never stop. And we didn't even know about it because we weren't logging the failures properly. So the question here is, really, honestly, the ultimate thing is, do you even need to be doing a call? Like, do you need a response to this? One way to do it is have a deferred reply. Have a deferred reply. So if you're talking one gen server to the other, you don't have to do the call inline and block with a receive. You can just tell the other guy, hey, do something, give me back a ref, and then in the handle info block, I can just match on that ref when it comes in. And then do something with the reply later, right? And so you can defer that reply possibly forever, but you can still work your queue without having to wait around for this one thing to show up. So this pattern is really, really good for things that, yeah, sure, a reply would be nice, but we don't necessarily need one, and I got shit to do, so I can't wait around for you. And then, of course, the big one, your code doesn't even need to be a process, right? Obviously, the big, the elephant in the actor room is that wrapping state in a process implies a mutex around that state. So any kind of access, read or write, is always mutex. There's no read-write lock. You basically just have to dig into, sometimes you just have to dig into Erlang's concept of shared memory, which is ETS. And so this is what we did with Folsom, by the way. So Folsom was having issues with basically updating counters at high frequency, and so we just said, screw it, we're getting rid of the processes and putting it all in the ETS. And hey, guess what, it worked. And then just refactor your code to pass around a PID, pass around a table reference instead of the PID. It sucks, but hey, that's the way it works. The network side, and actually I have some slides missing here, but I'll talk about them anyways. So one of the things that we found out with the Erlang distribution protocol that really screwed us over with our internal stuff, so we taught Erlang distribution internally to our other nodes. Erlang distribution protocol is tuned for low latency, so TCP no delay appears to be on by default because what we saw is anytime a single message would get sent out on Erlang distribution protocol would end up being one packet on the network. And so if we're sending a ton of messages over tons of tiny messages, each one of those is going to end up being a packet on the network, and your switch is going to die. And those are called runt packets. They're terrible. They're the entire reason that Nagel's algorithm even exists. So basically, what you have to do here, or what we found we needed to do, was you can do one of two things. You can either buffer in the gen server, which you're doing more work, but whatever, or you can actually use an intermediary process to do the buffering and then flush that out to deal with GC concerns. Or just open up a Gen TCP socket and send over that with Nagel turned on, and then that will help you with the throughput. But it won't help you with the latency. The other thing that I found out, this is actually recently, and I forgot to add it to my slides today, but TCP backlog Anybody here know what TCP backlog is? Yeah. So there's a queue. There's another queue here. So there's a queue in the TCP stack of the operating system for incoming connections, right? So if you have incoming connections, the TCP backlog is the queue of connections waiting to open. So these are half-open connections where you're waiting on your application to basically finish the connection and then open it up into a full socket, right, from the listen socket. And so the TCP backlog, on normal Unix operating systems, the TCP backlog is set to about 128, meaning that you can have 128 half-open connections waiting on your application to pick up. And as long as it doesn't get over that, you'll be fine. However, that option can be set in the BSD socket API. And for whatever ungodly reason, the default in Erlang when you use GenTCP listen is 5. 5 fucking connections. So you can only have 5 connections waiting in the queue. And so if you're doing high throughput stuff with a lot of clients, say 3,000, that all need to connect at once because you just restarted, you're going to have a bad time. And like you're just going to end up with a lot of connections that are just going to be just completely closed, and they're going to keep spinning on the other end, and it's just going to keep being hangups on that, closes on that connection because you don't. The operating system is like, well, I have no more room for you. And on modern operating systems, that number can actually be set to like thousands, right? Not that you'd really need that, but yeah, 5. So know the defaults because sometimes they're really bad. And anyways, in summary, if you're going to take something away from this talk other than nonsense, just grind the loop, right? So observe that there's a problem, find the queue that's overloaded, and then mitigate the bottleneck. And I mean, honestly, you could say a lot of stuff about Erlang, but at least it makes it really simple because at the end of the day, it's just a queue somewhere that's overloaded. So find the queue, fix it. And that's all I got. Any questions? I'm sorry, what's that?
Instead of setting the backlog real high, is it as good to use a pool of acceptor processes so that they each have their own?
It's in the operating system. So the setting, yeah. So you could get, there's no guarantees there, right? So like you could very easily get yourself. So it'll be fine for months. And then all of a sudden, like a bunch of stuff will happen, and then like a bunch of connections will start up, and then you'll have a customer complaining that they can't connect and they're stuck in a loop, and you won't know why, right? Because that's actually it's like it'll only show up in like netstat if you put in the listen option, because that's the only time it'll show you the listen queue, and then you got to know that it was set to 5 because. So the answer there is that. I mean, yeah, the typical way is to have an acceptor pool, right? To just pull stuff off, and that'll get you pretty far. I mean, we had this in production for 2 years with the default set to 5, and we didn't even know, right? It only just really screwed us in the past couple months. So you can get a pretty long ways, but honestly, there's no reason for it to be 5. It should just be, 128 at least.
Yeah, I'm kind of out of date, but I thought that the default in Linux had always been 5, so it sort of used to be that it's higher by default now.
Oh yeah, I mean, yeah, I'm not. Yeah, it might have been a long time ago that it was 5. I'm not sure. But when I checked the recent kernels, though, the default ends up being 128. So Unix archaeology should be like a thing. They should teach that in college. That'd be cool.
You made an argument for dealing with the backlog of the gen server queue to spawn the processes rather than giving it the worker pool. I'm wondering if the execution of that job is longer than the rate of incoming jobs, you can end up with the runaway spawn processes.
Yeah, absolutely. Yeah, exactly. Like, again, this is a degenerate case of 10 pounds of shit in a 5-pound bag, right? Like, there's a certain amount of capacity in the machine, and if you overload that, then you're done, right? Like, you buy more machines.
So why is worker pool worse?
Why is worker pool worse? Well, so the reason that I say worker pool is worse is because long-lived because you have long-lived processes that might be spitting off a lot of garbage, and instead of doing all the full sweeps on those, which would happen if a full sweep will happen every couple of GC cycles, right? And then reallocations will happen too. So you're doing all this work basically in terms of GC and reallocation basically for nothing, just because you have this thing sitting around instead of just springing it up and then throwing it away, right? So when you just spawn it up, the overhead is like, I don't know, like 300 and some bytes or whatever. But it's it's just a data structure in C, right? You're not spinning up a new thread, so it's fairly cheap. And I mean, yeah, it's got to go on a run queue and all that, and yada yada. So maybe the context switching will kill you. I don't know. That's why you got to bench it out. But the reason that I say it's better to spawn a process to do the work and then just throw it away is because you don't need to go through all those mark and sweep phases and all that other crap in GC. You can just it just throws away the whole heap and knows the bounds and just all back on. So it's less work in the end for the VM. So we use worker pools mainly just to wrap like connection stuff, right? Like we use Poolboy for our React clients and that sort of thing. I believe me, I've tried using worker pools for doing actual just generalized like CPU bound work, and it's just it ends up being more trouble than it's worth. Like you spend more time managing the goddamn pool, more CPU time managing the pool than actually doing yeah, it's awful.
I guess I'm wondering, how much does your application benefit from the OTE machinery, supervision, and automatic restarts and stuff like that?
Oh yeah, well we use hot code upgrade extensively. So hot code upgrade is great because it lets us, because we have 3,000 SSL connections on a machine.
Is there some reason you don't do that with socket migration and ancillary messages?
The hot code upgrade ends up being less complicated than all that. It's just, have these things, because I mean, these are connections we're taking in from the internet, right? So it's like, we have a public IP for each of the collectors. We GSLB across them from DNS, and then connections come in, and it's just a long-lived connection that stays open for a long time. And so that ends up being a pretty decent model for us. I mean, obviously it could be improved, but it ends up being a pretty decent model for us, and then just doing the hot code upgrades, it just works. So we end up with taking no downtime when we have to upgrade the code for these. Except when the hot code upgrades fail, and then we take some downtime.
You're doing proper Erlang releases then for the
What's that?
You're doing proper Erlang releases for the code upgrade.
We use like rebar and I mean, I wouldn't call them proper, but I mean we do use the release infrastructure. I would say abuse maybe. We number things based on like git rev and stuff like but we use rebar, and we use a lot of the chef stuff that Joe Williams put together for us to do the hot code upgrades. He put a lot of work in actually making that stuff usable, because it's pretty indecipherable sometimes.
And what proportion of your hot code upgrades actually succeed without any crashes?
Most of the ones without state transitions.
Yeah. What you don't need to use proper release.
Yeah, exactly. The ones where there's no state transitions. When there are state transitions, then you actually have to test the release, and that's just a big pain in the ass. Got to fire up a real one. Like you got to fire up the current release and then test it against there. Figure out why it's a big pain in the butt. So try to avoid those.
The comment about the Jan server call, the call timeout that you said. 5 seconds.
Yeah.
I know the history about it.
Oh, okay. The history about the 5 seconds. Yeah.
In the early days, the Jan server and the client, there was no monitor process time.
Oh, yeah.
So the server would crash while handling the request.
Right.
And that's why they had the timeout. But I would say nowadays it's always a bad idea to have a timeout on the client side.
Really? So you would rather?
You will detect if the server crashes anyway in the client.
No, I mean that's a good point. If it's a gen call, that's a good point. You'll detect if it crashes, right? So.
Or if it doesn't exist when you call, you will also.
But it doesn't detect the case where the gen server chokes on that bit of work and just spins.
No, but then it will deliver the answer afterwards, even if the type has
Fair enough.
and it will be out of sync somewhere.
Yeah, yeah. No, that's a good point. That's interesting with the history there. So for people on the internet, he was saying that the history of the gen server timeout is the fact that back in the day you didn't have monitors or links, and so if you had a gen server somewhere, it could crash in the middle of processing, and you had to have the timeout in order to keep the client from waiting forever.
There was actually links at that time.
Oh, there was links. Okay.
But you don't, link is double direction.
Yeah, the link is bidirectional instead.
You
Yeah.
don't want to crash the server.
Yeah, yeah. Right. Yeah, exactly. All right. Yeah.
I was thinking on your first slide, you had the tools you were using for debugging your system,
Uh-huh.
production system. Have you tried out Redbug?
Have I tried out Redbug? No. Oh, Redbug.
Yeah.
I have not tried out Redbug.
I can recommend that because it's built on top of the tracing MIPS, but it's used, intentionally it's used in the production system.
Oh, okay.
Because otherwise you can choke on the trace messages. But
Yeah.
so give it a try.
All right. Yeah. Right on. I'll give that a whirl next time things go
Also,
bottleneck. Yeah.
it contains some functions to get information from Yen servers and stuff.
Mm-hmm.
So perhaps you can find something useful there.
Sysget status will let you grab the state without having to deploy it.
Oh, without having to do all the nah. Cool.
You do have to guess it in a really, really annoying format. You have to delve about 4 different data structures deep into before you get to the actual state of the process. Very simple additions to OTP if somebody wants to make my Christmas card list. Get state turn, give me the state turn work, and run function over state and replace state with result.
Yeah. +1 on that. Yeah.
So you don't mention that for clustering, right? So it's very efficient that you send a lot of small packets, right? So that makes you try to open a socket to the nodes. So besides that, is any kind of bad observation for clustering, then makes socket connection is a better option.
I'm sorry. What was that? What do you mean by clustering? Do you mean like?
This is the Erlang, right? So we send to the nodes. And
Yeah.
For small packets, it's really inefficient, right?
Oh yeah, exactly. It's really inefficient and.
So besides that, is any bad observation for this clustering? So we should open a socket instead of use the default.
Yeah. So are there any other benefits to just opening a socket? Well, I mean, is there any other? I mean, you can certainly twiddle the knobs a bit in terms of send buffers. You can twiddle the knobs a bit in terms of send buffers. You get a little bit more control over it than you would if it was the Erlang distribution protocol. Yeah, exactly. You got to do the framing yourself. So I mean, it's a trade-off between code complexity and performance, right? Make the trade when you gotta. Anything else? No? Okay. Thanks.